Okay, this is the 10-3 notes for statistics honors. If you look at what we talked about in section 10.2, we basically were estimating the difference between two population means when standard deviations were equal, or in other words, approximately equal. So this section goes in the other direction and talks about when the standard deviations are not equal. So it makes sense that if when they were equal, we called them pooled, now we're going to call them non-pooled. So in your calculator, you would choose no for pooled. What is the logic behind this? Well, again, when you pool a test, it's because the standard deviations are similar, so we basically hedge our bets and say, if we pool it, it'll be sort of a happy medium between two very close values, which isn't a big deal. Now that the standard deviations are going to be very different, you don't want to do that. Instead, you want them to speak for themselves. And that means that S1 and S2 are both going to appear in this formula instead of creating an SP calculation, S of P. So basically, the sampling distribution for a non-pooled statistic, there are some changes that are going to be afoot here. With these changes, we start with the t-test statistic. So what's the same? The numerator. So remember, the numerator was this whenever we did the distribution. It was just that this was equal to 0 when we did the test, so we could eliminate it. So still, we're just going to have this x bar 1 minus x bar 2 in the front. The denominator is different. Again, why? Because we're allowing the standard deviations to speak for themselves instead of removing the subscripts, factoring it out, and then basically using a pooled standard deviation as a replacement. So the formula is kind of logical there, so that's not any different. Well, what is different? Well, this. So this crazy formula, one of the craziest you'll actually see in this class, is actually the computation for the degrees of freedom for a non-pooled statistic. So normally for a pooled statistic, remember we did n1 plus n2 minus 2. Well, that is not the case when it comes to a non-pooled statistic. Instead, we have to do this massive calculation. Just note this symbol delta right here is just another way to say degrees of freedom. So this is going to be a big deal in terms of test taking. Why? Because you have to be able to determine whether it's pooled or non-pooled. Once you determine that it's non-pooled, you're going to have to make the change to this instead of this. So just be aware of that when you're looking through and doing the test, that's going to be sort of a big change in terms of what you're going to be doing in the problems. Okay, so the requirements for a non-pooled t-test are very similar to the other ones. Basically, the only thing that's missing is the 4-step. We need independent random samples. We need normal populations for each. This is clear. Now we don't have any requirements for the standard deviations. We basically just treat them as individuals. So normally we just say the standard deviations are vastly different. You'll see the null alternative is the same for the pooled test. The test statistic, we just talked about that above. The denominator is different, but very logical to what it is. The numerator is going to be the same without the mu's in them that you do. So basically, very similar procedure that you're running. The big change is, though, going to be the degrees of freedom here that we're going to have to calculate. Okay, so why don't we start with an example here. It says the results of a state math test for independent random samples of students taught by two different math teachers at the same school are shown to the right. Can you conclude there's a difference in the mean math test scores of the students of the two teachers? Use alpha equals 0.10. Assume the populations are normally distributed. All right, so just getting started in terms of this. Assumptions, remember we need independent random samples and we need normality. It's worth noting that your n's are both smaller than 30, so we need to explicitly state that they are normally distributed, or we wouldn't technically be able to move on. Okay, so remember, this is going to be data set 1, this is data set 2, so if we're doing the null, remember a statement of equality, and it will never change. It's always going to be mu1 is equal to mu2. The alternative, well, what's the key word here that they say? Well, it says, can you conclude that there is a difference in the mean scores for the students? They don't mention one being larger than the other, so this is clearly going to be a two-tailed test. Okay, so right away we should be able to calculate t. Remember last time for the pooled test, we had to calculate the pooled standard deviation first because it was part of the formula. Now we don't have to do that. I'll rewrite the formula for you. X bar 1 minus x bar 2 over the square root of the first variance over the first sample plus the second variance squared, or the second variance over the second sample. Those would be the standard deviation squared. So all you have to do is take the data set that was provided over here, the summary stats, and sub them in. We're going to get 473 minus 459 over the square root of 39.7 squared over 8 plus 24.5 squared over 18. That is going to give us 0.922 as our t-test statistic. Okay, so once again, we know that once we have that test statistic, the critical value approach and the p-value approach are going to be the same, but because it's t, we always have to monitor what the degrees of freedom is going to be for the test. So remember, for this one, it's this monstrous value. So we're probably going to stick with the p-value approach using TCDF just because it's a little bit simpler, but obviously know both methods. But before we can do anything, we need to know that degrees of freedom because it's required in order to use either approach. So we're going to have to calculate that. So at the bottom here, the first thing we want to do is just figure out what this delta value is going to be. So it's a big calculation, but we'll do it. So I'm going to write out the formula over here. So it's going to be, actually, hold on, it's a little bit massive of a bracket. So we're going to be doing the first variance over the sample size, plus second variance over the sample size, all squared. That's going to be over the variance again, divided by the sample size squared, divided by n1 minus 1, and then the, again, variance squared over n2, all squared, for n2 minus 1. Lots going on here, obviously, that you're going to have to plug in numbers. So again, what are we doing? We're taking these values right here, right? And we're going to be plugging them into this massive looking formula. So let's do it. So we're going to get 39.7 squared over 8 plus 24.5 squared over 18. All squared. Then we're going to get on the denominator, we're going to get 39.7 squared over 8 all squared divided by 8 minus 1. And over here, we're going to get 24.5 squared over 18 quantity squared divided by 18 minus 1. So obviously a lot going on there. Mimics this formula perfectly, right? That's all we're using. Just because the calculation is an absolute debacle, I'm going to, hold on a second here. I'm going to give you the calculation. So for some reason you're not getting this, I'm going to give you what you should get in the numerator and denominator when you do them, because I doubt you're going to be doing them all at once, because that would be one massive set of parentheses, groups of parentheses. So if you do it, you'll get this, which is going to give you approximately 9.459. Okay, so a couple things here. This is the degrees of freedom. Note that We have some options for what we can do. So if we were going to go to the critical value approach, so the critical value approach, right? Then we would need the degrees of freedom to be in a whole number, essentially. Because if you go to the t-table, all the df's on the left and right side are whole numbers. So we would just round it to wherever it would go. No special idea, but or a special rule like some of the other scenarios. So we would just say df is 10. But if we go to the p-value approach, it would be in our best interest to use 9.459 because we're basically using TCDF and it allows us to use decimals. So that's going to give us the most accurate result. Another reason why I like to use TCDF. So that's what we're going to do actually. I'm going to go with the p-value approach here, p-value approach. So remember, this is a two-tailed test. Because it's two-tailed, we're going to need a shadow copy of this. So first things first, 0.922 is going to be our t-value. So we're just going to plop that on here, 0.922. So that means the area over here in the tail would actually be half of that value. So we have a shadow value over here of negative 0.922. And that area. So we have to when we do our CDF, we basically have to double it, just like we've been doing. So let's take care of that. So we're going to get p-value is equal to 2 times TCDF of 0.922 to a large number to the right with 9.459 degrees of freedom. So you can see it allows us to put this in here. It allows us to actually use in a more exact value. So we're going to get 0.3794 in your calculator. If you do so, that means we're comparing this to our alpha in this problem. So just a note, alpha is 0.10, which is pretty large, but still this 0.3794 is larger than that. So we would say we do not reject H naught. Okay, because we do not reject H naught, that means we're accepting that the test scores for the two teachers are the same in this scenario. Okay, so let's try another example of the non-pooled test. The annual earnings of independent random samples of 19 people with a high school diploma and 16 with an associate's degree are shown to the right. Can you conclude that people with an associate's degree have a higher mean annual earnings? Use alpha 0.01, 1%. Assume the populations are normal. Okay, so just right off the bat, you can see independent random, normal. Obviously, we need the normal because the sample sizes are 19 and 16. We're basically comparing the earnings for people who just have a high school diploma versus students who have moved on to an associate's degree. All right, so again, this is our second population. Start with the null, which is always the same. It's that the two population means are identical or for this scenario. The alternative, okay, so another one that can be a little confusing. It says, can you conclude that the people with associate's degrees have higher mean annual earnings? So they're stating that this side is larger, which means that our first diploma, the high school diploma, is going to be less. So we would say mu1 is less than mu2. So just again, be careful with that. Students often mess this up because they're quickly going through it and they're seeing higher words like last time when they talked about the amount of time the machine, it works faster. Words sometimes are misleading when it comes to that stuff. So just be careful with that. Okay, so one of the things to note here is on an exam situation, you might not necessarily be told whether it's pooled or non-pooled. If you look at the standard deviations here and here, you can see that these are not even in the same ballpark. One is actually almost double the other one. Now note, believe it or not, in terms of statistics, a 2-to-1 ratio is often, or at least a 2-to-1 ratio is often the requirement for a non-pooled scenario. I don't know if they mentioned that in the book or not, but it's something that I've learned in the past, so worth noting that that's often a sort of requirement for that. So in this scenario, just as one is significantly larger than the other, so we're going to go in the non-pooled direction. So here we go. So our test statistic we want to calculate first. So remember, we're taking the means, 329,493 minus 40,907 to begin with, over the square root. Remember, no more pooled standard deviation, so we're going to be taking our first standard deviation, squaring it, dividing by sample size, plus second standard deviation, squaring it, creating a variance, divided by 16. When we do that calculation, we're going to get negative 4.954. Okay, so just to be clear here, hold on, don't want to be sloppy. So negative 4.954 is our value. So at this point, we can say, all right, well, we could literally go to TCDF and figure out this p-value right away, but we have one thing in our way in a non-pooled statistic. We need to figure out the degrees of freedom, and it's not going to be 19 plus 16 minus 2. Instead, it's going to be our delta calculation. So here we go again, a very large calculation. So we're going to get 3118 squared over 19 plus 6162 squared over 16. Okay, like this. And then we're going to have 3118 squared over 19 all squared divided by 19 minus 1. And then we're going to do the same thing over here. 6162 squared over 16 all squared divided by 16 minus 1. Okay, if we do this, we are going to get some very large values. So this is going to be about 8.322 times 10 to the 12th. Over here, we're going to get about 3.899 times 10 to the 11th. When we divide these values, we get around 1.34. Okay, so basically, again, once we get this value, we could go right into TCDF. This time, we wouldn't double it, right? But you could also go to the critical value and figure that out. I'm just going to give you a critical value example because why not? So that you understand. Last time we did the p-value, but let's do a critical value because you've done this a lot, but just in case. So if we're going in the critical value direction, we want to use degrees of freedom. We'll just round in the logical direction. We'll say the degrees of freedom will be 21. So what do we have to do? Let's draw our graph. Okay, this is a left-tailed test, so we're looking for a critical value on the left side. We know that alpha is 0.01. We only need alpha because this is going to be a negative t sub alpha value, 0.01. We don't need alpha over 2, and it's going to be at 21 degrees of freedom. Okay, so let's take a peek at that. So this is from our previous problem. We'll get rid of this, and we'll go over here and say, okay, t.01, and we're looking at, what's the degrees of freedom again? 21. Right. So we're on the wrong page. There we go. So we're looking at 21, and we're looking at t.01 degrees of freedom, which is going to give us, it looks like, 2.518. All right, back here. So negative 2.518 because we're over on the left side there. So we know, as always, rejection region over here. We do not reject anywhere else that's not in the tail. In this case, there's 1. So we take our t value, which is at t equals negative 4.954. It's in the rejection region of this graph, so we reject h naught. Okay, worth noting, if you had done the TCDF, you would have gotten a p of approximately 0.0003, so approximately 0 in terms of our table at least. So you can see that we would have rejected by a mile, as we do here, our t-value significantly less than the critical value on the left side of the table, so we reject h naught. What are we saying when we reject h naught? We're basically rejecting that having just a high school diploma versus an associate's degree would result in equal earnings. So this is saying that if you don't get an associate's degree and you just have a high school diploma, then you're likely to earn less in terms of earnings. Okay, so what about the non-pooled confidence interval? So same idea. The non-pooled interval, same assumptions as the non-pooled test. We're looking for standard deviations that are vastly different. Again, we're going to need to use this formula here in order to determine the degrees of freedom. Why do we need the degrees of freedom? Because we need to find T alpha over 2, which is in the formula down below. You'll see the formula is almost identical, except for this part right here, which is going to be, again, the denominator of this test statistic, just like it was in the pooled test. So, or pooled interval. So let's look at an example. It says, now return to the state math test from the original problem. So remember, these are the teachers' scores for the teachers, each teacher in the same district. Obtain a 90% confidence interval for the difference mu1 minus 2, mu1 minus mu2 between the mean scores of students taught by the teachers. Remember to interpret the interval. Okay, so let me just write out the formula here. We got x bar 1 minus x bar 2. We got plus or minus. Remember in this problem that we're looking at a, looks like a 90% confidence interval. So if the confidence interval is 90%, that means alpha is 1 minus that, which is 10%. We need alpha over 2, which is going to be 0.05. So that means we want t sub 0.05, and we're going to multiply by variance over the sample size plus second variance over that sample size, all with a square root from their sum. Okay, so again, it's all about just plugging in numbers. So 473, 459, plus or minus. If you look up T.05 in your table at the degrees of freedom, remember that if we go back all the way to our math problem here, remember we calculated the degrees of freedom to be 9.459, but we use df is equal to 10 when we have to use the table. So let's look at that. So 9.459 degrees of freedom is 10. So we'll say degrees of freedom is 10. So if we go into the table at T.05, at degrees of freedom 10, let's get rid of all this. 5 at degrees of freedom 10, we get 1.812 as our value. So 1.812, and then square root of, and then we just more subbing in numbers, 9.7 squared over 8 plus 24.5 squared over 18. If we do the calculations, we're going to get 14 plus or minus 27.503, which is going to give us an interval of negative 13.503 to 41.503. Okay, so in terms of this interval, we obviously would like to interpret it. Remember that is a common thing here, so why don't we do that? So we would say we are 90% confident that the difference in mean scores is between negative 13.503 and 41.503. Okay, so a small thing about this. Students will often be a little confused when it comes to this and this. So note we have a negative now. So we didn't have a negative the last time we wrote out the interpretations when it comes to differences. So what does that mean? So that means that it's anywhere from teacher 2 being 41.503 higher than teacher 1 to teacher 1 being 13.503 higher than teacher 2. Okay, that is, if you need to play that back again to hear that again, that's fine. But that is the scenario, is that this is implying that they're not sure which one is larger in this scenario, because one's negative and one's positive. Just a small side note, when you do this on the TI calculator, because the degrees of freedom calculation for a non-pooled scenario or distribution is going to be it could be rounded really easily, and there can be some error. You're going to find that some of the answers for the intervals will be a little different than your actual calculations. So just be careful of this when you're doing stuff on MyStatLab and things like that. Okay, so the time has come again to point out a very important concept. So remember, if you have an interval that is a certain confidence level, let's say 90%, and you have a two-tailed test that is 1 minus that confidence level, or in other words, 10% significance, then you can use the interval to make a judgment about the test. So for example, if we go to this test tool, remember our first problem that we did, we were basically testing these teacher scores, and we said we have a two-tailed test here at 10%. So we can use a 90% confidence interval with the same data to make a judgment about this hypothesis. So I'm going to rewrite it down here in our problem. So again, we were told that the hypothesis was mu1 is equal to mu2, and the alternative was mu1 is not equal to mu2. So since this is 10 per alpha equals 0.10, and our confidence level for our confidence level for this interval is 90%, and their sum is 1, that means we can use this confidence interval right here to make a judgment about this hypothesis test. So what's the judgment? Well, again, the top value represents mu1 minus mu2 is equal to 0. So it's claiming that 0 should be in the interval. So if you go up here, you can clearly see that 0 is in this interval, which means we are going to support the null hypothesis and claim that that is true. So what do we say? We would say we do not reject H0. Okay, so if you recall, we go all the way back to this problem, right? What happened? In the end, we decided to do not reject H0. So the test and the interval create the same result again, but that only occurs if it's a two-tailed test, and the interval and the confidence level and the significance have a sum of 1. It's the only way you can do it. So again, keep that in mind when you're doing these tests, because every once in a while you will be asked to use just an interval to make a judgment about a hypothesis test.